Hello, I'm Renee Carter, one of the co-creators and vice president at PixelEXX Systems. At PixelEXX, we're fundamentally changing the way we collect and measure light, designing image sensors to work in complex, uncontrolled environments while collecting more photon information. There are three big pushes in the industry: developing smaller, more energy-efficient image sensors, enhancing image performance, think ultra-high resolution, wide dynamic range, and expanding sensing functionality, such as multispectral imaging. The challenge is that improvement in any one of these areas requires compromise in the others. The underlying problem is a result of how we collect and measure photons, something that hasn't fundamentally changed since the first digital cameras. The signal depends on both the number of photons you can collect and the ability to convert those photons into electrons, quantum efficiency. The challenge is that as we linearly scale the pixel size, the amount of light incident on each sensor reduces quadratically. As a result, for applications that demand greater contrast and clarity or are implemented in light-starved conditions, larger pixels are required to maximize the signal. Collecting more photon information enhances object identification and target discrimination, but challenges the system. Filters decrease photon flux on the detector. The monochrome sensor collects intensity information and has a maximum quantum efficiency of 70%. With the addition of spectral and polarization information, the quantum efficiency plummets to below 20%. Despite these challenges, leading manufacturers are racing to develop submicron pixels. The left side is work by Samsung, modeling 400, 600, and 800 nanometer pixels. They report that while submicron pixels can improve resolution, there is a significant degradation in performance at sizes below 450 nanometers. On the right are absorption profiles from 60, 80, and 100 nanometer Me photosensors. These sensors are designed to induce Me scattering, enabling large absorption cross-sections. The geometry of the pixels determines the peak absorption and the wavelength selectivity. No filters are used. This slide demonstrates the physics enabling the PixelEXX sensor. Light absorption is determined by sensor geometry. The power flow lines in panel 1 show that violet light is strongly absorbed in the middle sensor, but only weakly in the narrow and wider sensors to the left and right. Panel 2 is an electron micrograph showing one step in fabricating these sensors. We are utilizing this physics to transform imaging and sensing. Our core patent was granted last year with broad claims. As you can see in our product roadmap, we've leveraged significant non-dilutive funding. We will have test arrays this summer and expect a beta camera by the end of 2024. We are currently raising $2 million to support development and commercialization efforts. And with that, I'd like to thank you for your time.